Now we'll develop the equivalent circuit for three-phase induction motor. The three-phase induction motor consists of two magnetically connected systems, the stator and the rotor. This is similar to the transformer that has also two magnetically connected systems, the primary and the secondary windings. The stator is supplied by balanced three-phase voltages that drives the three-phase currents through the winding. The current induces a voltage in the rotor. The induced voltage V1 across phase A is equal to the sum of the induced voltage E1 and the drop across the stator resistance and the reactance I1 R1 and I1J X1. We have the equivalent circuit, which is V1, which is equal to E1 plus the drop across R1 and JX1. This is the part for the eddy current and the magnetizing reactance JXC and RC. For the rotor, we have I rotor, rotor resistance, and rotor reactance JXR, and for the rotor voltage ER. We have I naught equals IC plus IM, the magnetizing current IM, and the core loss component of the current, which is IC. The induced voltage in the rotor at standstill at S equals 1 is equal to 4.44 NR times phi times the frequency of rotor. Now the frequency of rotor is equal to the frequency of the stator as S equals 1. Which is FE. If we need to get ER at any slip, FR will equal to SF stator. Then we have E rotor equals 4.44 times NR times phi maximum times F rotor, where we can substitute by F rotor by SF stator, SFE. We have E rotor equals S the slip times the rotor voltage, rotor induced EMF at standstill, which is ER naught. We will study the rotor circuit alone. We have E rotor, R rotor, and JX rotor. We can get I rotor, IR equals E rotor divided by R rotor, the JX rotor. E rotor equals S E rotor at standstill, and for the X rotor is equals to S X rotor at standstill. We can divide the numerator and the denominator by S. Then we have IR equals E rotor at standstill divided by R rotor over S is a JX rotor at standstill. The rotor circuit can be represented as follows: E rotor, which is E rotor at standstill, JX rotor, and R rotor over S. R rotor over S is composed of two resistances. The first resistance is R rotor, which is the rotor resistance, and the second one is R rotor times 1 minus S over S, which is a fictitious resistance that represents the mechanical load. R rotor over S, JX rotor, E rotor at standstill, and the rotor current. And for the stator circuit, R1, JX1, I1, and V1 for the supply voltage and current, R rotor resistance to eddy current, and JXM, which is the stator over the hysteresis losses in the stator. For the transformation of the current, we have I2 by the transformation of the transformer. We have I2, which is the referred rotor resistance current to the stator circuit, equals to I rotor divided by the effective turns ratio of the induction motor, which is the number of turns of the stator divided by the number of turns of the rotor. We can transfer the impedances by the ratio A effective square. For R2 and X2, we get R2 equals A effective square times R rotor, and X2 equals A effective square X rotor. These are the two resistances obtained as referred to the stator side. Uh, Now we will discuss the power or power flow diagram. We have the input power. The first power loss is a stator copper loss in R1. Then we have the core losses in RC, which is P core. The remaining power is called the air gap power, which is the power that passes the air gap to the rotor. The first losses in the rotor is the power copper losses in the rotor. Then we have the converted power or P converted, which is the power available for conversion to mechanical power. Part of this power is lost as mechanical losses, friction and windage, and the rest is the output power. For the input power equals to root 3 V line I line cosine theta, or 3 V phase I phase cosine theta, which are the voltages and the currents of the stator. We have also the rotor resistance. We obtain the rotor copper loss F rotor. I'm sorry, P rotor copper loss, and the friction and windage losses. Uh, this is rotor copper loss, friction and windage losses. We have also the copper losses of the stator, which is stator copper loss. Now, from the equivalent circuit and power flow, we have the input power, which is the three-phase power P input, 3V phase I phase cosine theta, or root 3 V line I line cosine theta. The first losses are the stator copper losses and core losses. Then we have the air gap power, which is going to pass the air gap to the rotor. Then we have rotor copper losses taken away as heat energy loss. Then the left part of power is the P converted, which is the part converted to mechanical power. Part of this power is lost as friction and windage in the bearing and the air movement around the rotor and the fan. Then the rest of the power will be output to the load, which is the P out. The approximate circuit for a phase of a single phase, we have V1, I1 are the stator voltage and the current, rotor, stator resistance R1, which accounts for stator copper loss, the magnetizing reactance of the stator coil, then the magnetizing reactance that represents the eddy current. Then we have the air gap power, which is going to pass the air gap to the rotor. We have rotor resistance, which accounts for rotor copper loss, and the fictitious resistance R2 or R rotor R2 times 1 minus S over S, which accounts for the output mechanical power or the converted power. For the approximate equivalent circuit, we have P air gap equals P input minus stator copper loss, or equals to 3I2 dash or I2 square R2 over S, which is the power for these two resistances. The equivalent of these two resistances is R2 divided by S. This is R2 divided by S. And for the converted power is the power which is going to be converted to mechanical power in this resistance R2 times 1 minus S over S, which is equal to 3I2 square times the resistance R2 times 1 minus S over S, which is the difference between the air gap power and the rotor copper loss. Now for the output power, which is equal to the power available for conversion to mechanical power minus the core and friction and windage losses. Last but not least, the torque developed equals to the power converted divided by omega m, which is the power air gap times 1 minus S divided by omega S times 1 minus S, or the air gap power divided by omega S. We have ratios between the power air gap to power rotor copper losses RCL. This is air gap to power converted. We have the ratios are 1 to S to 1 minus S. If we need to get power converted, we multiply 1 minus S times the power of the air gap, and we need to get rotor copper loss. We multiply S times the power of the air gap. Now we will see the torque speed characteristics of the three-phase induction motor. We have torque as a function of S. We have the pull-out torque, which is the maximum torque that can be given by the induction motor. For the linear region or the low slip region, the S from 0 to S at maximum torque, we have the relation between the torque and the slip is a linear relation. As we increase the slip, the torque increases. This is a direct relation part with the torque, between the torque and the slip. And for the part from S maximum torque to S equals 1, which is a no load at the starting torque, we have the relation between the slip and the torque is inverse relation. As we increase S in this direction, we will see that the torque is decreased. This is for large values of S. The torque is inversely proportional to the slip S. And the point of operation here is a point at full load torque. And the point at 0, S equals 0, this is the no load torque or the no load condition. Now we will see another example. Example number 2, 480 volt, which is the V line, is the line voltage. 50 horsepower is the output power. Three-phase induction motor draws 60 ampere, which is I1, the current of the stator, at 0.85 lagging power factor, which is cosine theta 1, the power factor of the stator. The stator copper losses equals 2 kilowatt. This is a stator copper losses equals 2 kilowatt. The rotor copper loss equals 700 watt. This is the rotor power. Rotor copper loss equals 700 watts. And the friction and windage losses equals 600 watt. This is the friction and windage losses. The core losses equals 1800 watt. The stray losses are negligible. The required are the air gap power, P air gap, P converted, output power, P out, and the efficiency. First, we need to get P air gap. First thing we can get, which is the P input, root 3 times V terminal or V line, I line cosine theta, all are given. Root 3 times 480 times 60 times 0.85, all given in the problem. We have P input equal 42.4 kilowatts. For the air gap power, we subtract the stator copper losses, core losses from the input power. For 42.4 minus 2 kilowatt, which is the stator copper loss, and 1.8 kilowatt, which is the core losses, we get 38.6 kilowatt, which is the air gap power. This is the first required. Second required, power converted equals the air gap power minus rotor copper losses. 38.6 minus 0.7, we have 37.9 kilowatts. For the output power equals the power converted minus friction and windage losses. 37.9 minus 0.6, we have 37.3 kilowatt, which is the output power. And for the efficiency equals the output power divided by input power. 37.3 divided 42.4 times 100 equals 88%. Example number 3, we have 460 volt, which is V line of the supply, 25 horsepower, which is the power output, 60 hertz frequency of the source. The number of poles equals 4 pole. Star connected induction motor has the following impedances given: R1 of the stator, X1 of the stator, R2 of the rotor and X2 for the rotor. We have Xm for the magnetizing reactance. The total friction, rotational losses, friction and windage, including the core losses, added to it the core losses, is equal to 1100 watt for slip equals 2.2%. The required is the speed in rotor or in motor, stator current I1, power factor of the stator, power factor 1, converted and output power P converted and P out, induced torque and load torque T induced and T load, T load or T out, and last but not least the efficiency. First, we got the speed. We got NS equals 120 times frequency divided by the number of poles. 120 times 60 divided by 4. We have 1800 RPM is the stator field speed. Then we got Nm, which is equal to 1 minus S times the NS, 1 minus 0.022 times 1800 equals 1760. We got the total, which is the series equivalent of these impedances, R2 over S, which is the equivalent of these two resistances, plus JX2 in parallel with JXM. Then the equivalent is in series with R1 plus JX1. We got the total impedance 14.07 angle 33.6. For the current, we divide the phase voltage, which is the line voltage divided by root 3, V phase, equals V line 460 divided by root 3, which is equal to E value, divided by Z total. We get I1 equals 18.88 angle negative 33.6. For the power factor, we get the cosine of the angle of the current, cosine 33.6, and the sine of the angle is negative. Then this is a lagging power factor, which is equal to 0.833 lagging power factor. We now can get P input, which is equal to root 3, 480, I'm sorry, this is 480. Root 3 times 480 times the current I1 times the power factor 1, we get the input power equals 12.53 kilowatt. For the stator, copper loss is equal to 3I1 square R1, which is 3 times 18.88 square times R1.641. We have the stator copper losses equals 685 watt. For the air gap power, we subtract B input minus stator copper losses, 12,530 minus 685 equals 11,000 or 11,845 watt or 11.845 kilowatts. To get the power converted by the ratios, we have P converted equal 1 minus S times the P air gap, 1 minus 0.022 times 11.845 kilowatts. We got P converted equals 11.858 kilowatts. For the output power equals power converted minus rotational losses, 11.858 minus 1.1 kilowatts. We have P out equals 10.485 kilowatts. The torque induced equals the P air gap divided by omega S. We divide P air gap 11,845 divided by omega S, which is 188.5. We get T induced equals 62.8 kilowatts. And for the torque output, we divide P output by omega M, 10,845 divided by 184.4. We got torque output equals 56.9 Newton meter. The efficiency is equal to the output power divided by input power times 100, which is equal to 82.7%. Thank you for today. See you in the next lecture.